Hello guys, how are you doing? So let's start this problem today. Let me see if this is recording first, because it wouldn't be the first time that I record the whole lesson, or I think in recording it but it's not recording. So we keep going with this series of problems in force method or superposition method for solving statically indeterminate frames in this case. For this particular problem, the first thing that you have to identify, well, the problem is asking draw the axial, shear, moment diagrams, but the first thing that you have to identify here is what are we gonna do? So we have three unknowns here, three reactions, AY, AX, and MA. And this is a roller, so we have another reaction here, BY. And no matter how you do this, you can count the number of reactions and the number of equations. You can say 1, 2, 3, 4, 4 reactions, 3 equations, statically indeterminate of first degree. You can do the method of reactions has to be equal to 3 times the number of bodies. So if you consider this only one body, 3 times 1 is 3, so that's why, and the reactions are 4. Statically indeterminate of first degree. So the method of the force, or the method of the superposition, the first step is select a redundant. A redundant reaction is one reaction that is in excess, if you will. That reaction is not going to affect the stability of the structure, and the structure is still going to be in equilibrium. So we have to identify which one is the reaction that we could use. For example, let's say that I take out, I don't know, BY. If I take BY out of this problem, this is still a cantilever structure, and it's stable and it's statically determinate. So I could do that. I can take out this moment, and if I take out this moment, this will become a pin, this will become a roller, and then the rotation will be the one that I'm taking out as a redundant. For this particular problem, I'm going to, but if you take out AX, for example, this is going to be able to roll in this direction. There's nothing holding it in that way, so that means that it's not going to be stable. So for this particular problem, I'm going to select BY as a redundant. And if we do that, then we have to do a new drawing of our primary structure. Our primary structure will be this. Everything is going to be the same, exactly the same as before, except I'm eliminating the support reaction, BY. And this is what we have. Same distances, same everything. This is 20. This distance here is 20. 20, and this is 15. Meaning this distance here is 25. 345. 345. 25. 25 feet. And based on that, we proceed to calculate the reactions in our primary structure. Remember, this is called the primary structure. Okay, how do we calculate the reactions? Whatever way you want to. Summation of moments at A equals 0. Let me use the blue for that. Summation of moments at A equals 0. Then you have this 20 times 1.5, 1.5 times 20. And remember, this is going to be like here, 20 times 1.5. And the distance from here to here is 10. And then you have this 10 and this 15. So it's going to have to be 1.5 times 20 times, I'm going to put it like this, so when you review, you know what I'm talking about, 10 plus 15. And what else? Nothing else. MA, this is positive, this is negative, minus MA equals 0. And then we can calculate MA as 750 cubic foot. Moment reaction calculated. Then we can do summation of forces in y equals 0. So if I do summation of forces in y equals 0, I have AY minus 20 times 1.5 equals 0, so AY equals 30 kb. And of course, because I don't have any reaction in the x direction, AX is 0. Okay, this is the what it is. Now, the idea is this: take this out once again, and maybe I should have done that before. I'm gonna do it here, just explaining the principle. If I'm interested in finding this, what I'm going to do is this: I'm gonna take this out, and by doing that, I know this point is gonna deflect in this direction. It's gonna deflect something like this, and it's gonna become, I don't know, this is gonna be something like this, something like that. It's gonna come down like that. Now what do I have to do? Of course, it's gonna be inclined and whatever. So what I'm gonna do now, I'm gonna get this, I'm gonna get this other structure, and I'm going to push it up. When I push this up, it's gonna go back to the original position that it was before. And of course, I push this out with a value of 1, and then once I calculate this part, which is gonna go whatever here, this is gonna be FBB, which is gonna be the flexibility coefficient. So this deflection here is plus this FBB times By has to be equal to 0, and then we can solve. This is plain and simple virtual work method as we studied before. So let's do that. Now I need the virtual structure here. Virtual structure is going to be exactly as the primary structure, but now is when I push it up with 1. This part corresponds to this part. What I'm doing here is this part, pushing it up with a value of 1, with a force of 1. And the distances are the same distances everywhere for this part. So then I need to calculate my equation for the moment, etc., etc., etc. And that's exactly what we are going to do. Now, let's summation of moments. If I do this, okay, summation of moments at this point A, this is gonna come in this direction, right? It's gonna need a moment in this way. Now it's gonna be 1 times 20 plus 15, 35. So this moment is 35 in this direction, and at the same time, summation of forces in y equals 0. That means that this reaction here is gonna be 1. I know that I'm going to need my reactions in this local coordinate system, so I better convert that in 2 reactions here. This one here in this direction, and this one here in this direction. And if this is 1, I know this angle here. That angle there is going to be 53.13 degrees. Why? Because it's the inverse tangent of 20 divided by 15. And you can work that with triangle relations also, but I realized that the majority of the students get confused with those triangle relations. So I rather using angles for this approach. So if this is 53.13, this is 36.87, and this one here again is 53.13, meaning this force right there is going to be 1 times cosine of 53.13, and cosine of 53.13, cosine of the answer, is 0.6. That means that this is going to be 0.6, this is going to be a sine of 53.13, which is 0.8 right there. And we already have this part done. I should have done the same thing here, but I'm going to do it in this space that I have. so it doesn't become that crowded, the drawing. So we have this moment, and that moment is 750, and on top of that we have this reaction AY, which is 30. Same approach, same thing. That 30 I have to convert. I know this angle, 53.13 degrees. So that one, I'm gonna decompose it in this one and in that one over there. Same. This angle here, 53.13, because this is 90, this is gonna be 36.87, and because this is 90 again, this is gonna be 53.13. Now this force here is going to be 30 cosine of 53.13, and 30 cosine of 53.13 is 30 times 0.6, which is 18, and this is 30 sine of 53.13 because it's equivalent of reading this side here, and the sine is 0.8, so 30 times 0.8 is 24, and then we have that those reactions over there. Don't forget about the load that we have on top of that. And we have all the distances. Now, what is the next step? The next step is applying the equation. What is the equation? We need the moment we need to calculate first the displacement in the primary structure, and then we have to calculate the flexibility coefficient in the virtual structure. So how do we do that? We have to define how we're gonna work this out. What are gonna be our x? I think that is way easier if we consider in our local coordinate system like that, and I start my first cut here from left to right, and in the same way I make the second cut here. Let's say this is cut 1 1 and this is cut 2 2, but then my x is gonna come in this coordinate system in this direction, which I could have used this one also, but I find it easier to measure it in this way. And same thing here, 1 1 and 2 2. I'm gonna be measuring x here, and I'm going to be measuring x in that direction over there. Okay, for the first part, for 1 1 here, if I make that cut, we don't have to do this every single time. I think that at this time you have practiced a lot, but I'm gonna just do this cut really quick. Like there, and this is 1. So if we are interested only in the moment, because at the end, remember what are we doing? We're doing the integral of mm, or small caps, divided by ei dx. That's what we have to do, the summation of all of them. So I need these equations. Summation of moments here, this is x, so I have 1 m equal x. I have my equation for that, for 1 1, remember, and 1 1 goes between 0 and 20. And for my second cut, my cut 2 2, what we have is the only thing that well, not the only thing, but one of the things that you have to be really careful when you do this part is that because I'm approaching from this side of the beam, now I'm gonna do this drawing again. I was all for saving trees, but I'm gonna do that drawing again here. I'm gonna kill, I'm sorry, tree. I'm gonna do it here. So if I do this cut in the virtual, that's what I'm doing. Cut 2 2, which by the way goes from here to here, and that here to here is expressed from 0 to 25 because this distance is 25, and I need those limits. So the important thing here, not the only important thing here, but one of the important things here, this is 0.6, this is 0.8, and this was the original one that we had before. But because I'm using this side of the beam, now be careful, because the shear, the positive convention for the shear and for the moment is this. Not like that, but like this. If you don't do that, your signs are gonna change and you're gonna end subtracting or adding things that you shouldn't be. Now when you do summation of moments at this point, basically what you have, and I'm forgetting about this 35 here, 35 moment over there, this moment. So when you do summation of moments here, you have negative moment, let's pass it to the other side, positive moment is gonna be 35 minus 0.6 times x. So that moment is going to be 35 minus 0.6x. And that's going to be the moment in the virtual for 2, 2. Okay. Now, same thing we have to do here. For the first case, in the primary structures, for the first case, this is what we have. And the first case, I mean 1, 1 from 0 to 20. 0 to 20. And this is the what we have over there. So in this end, I'm going to have my shear, my moment. Now capital shear, capital moment, because this is the way we refer to in the primary structure. And we're going to do summation of moments at this point. This is x. So then you have m plus, that means it's going to be negative. I pass it to the other side, right? M is going to be minus this value, 1.5. This is the value of the load, 1.5 kilonewton, times x. That's the load here, 1.5x. And the distance is x divided by 2. So it's going to be minus 1.5 x squared divided by 2. That's the value for the moment in the first part. And for the primary, in the section 2, which goes from 0 to 25, and remember 0 to 25 is from here to here, okay? 0 to 25, let's see what we have. We have is this section here, which is going to be treated in the same way that we treated the other one. I'm going to do the drawing. This is going to be 18. This is going to be 24. This moment here is 750. And now when I put my accepted positive convention, because I'm using this side, my local system will be like that. So but I'm measuring from this side. Now that means that I'm looking at the other side of the beam, and this is going to be shear, and this is going to be m. So if I do summation of moments at this point, and this is x, of course. So if I'm doing summation of moments at this point, I'm going to have negative m, pass it to the other side, positive m. Now I have negative 750 plus 18x. So it's going to be 18x minus 750. I already have that part done. So now we have this completed. What is the next step? The next step is calculating this deflection. That's the first step. How do we calculate that deflection? The deflection in the primary structure is going to be equal to because EI is constant, it doesn't say anything here. I should have said it from the beginning. EI constant. Then I can take this out of the equation, EI. So it's going to be 1 over EI times the summation of this. This is the virtual x, 0 to 20. Small m, x, times big M, this one, negative 1.5 x squared divided by 2 dx, plus the other portion, this one, for the section 2, remember these correspond to the section 1, and this will be M. That's what I said. Now from 0 to 25, 0 to 25, 0 to 25. Then you have a small m is this one. Big M is this one. The X. Solve this. You can solve it. You have a calculator. I'm not gonna waste time of the video because then people see the videos too long and they get bored. So, but you can solve it. You can have fun solving it, and then you can get the deflection at that point B, due to the elimination of the redundant force, will be negative 405,000 divided by EI. Now, negative sign means that you are putting the load going up and the deflection is really going down. That's all that it means. So the deflection in this case will be opposite to this one, but it's okay, it doesn't matter. Now, for the virtual, this is for the primary structure. Now let's calculate that push up now. Push up meaning this part here. That's what I'm doing. That push up for that part. And it's going to be the same thing. So that flexibility coefficient, which is also called like that, and you can say, oh, this is the deformation of the virtual structure when it's pushed by a unit action in the direction of the displacement. It's the same thing. It's going to be equal to 1 divided by EI multiplied by the integral of, let's go back. Now it's only virtual versus virtual. This is again virtual versus virtual. So it's going to be from this part, 0 to 20, of a small m times small m times small n. So it's m times m, which is the same thing as saying m squared, which is the same thing as saying x squared dx. Plus, this is for section 1, for section 2, now we are in the virtual structure, which is this one here. It's a small m times a small m, which is the same thing as saying m squared, which is the same thing as saying this. Dx from 0 to 25. And when you solve for this, then you get the FBB is 22,041.67 divided by EI. Now, the method of the consistent deformations, which is the same method that we are using, we know that the total deformation at that point is 0. Why? It has to be 0 because it's a roller at that point. So if this is 0, when I combine this deformation, which is negative 405,000 over EI, plus, now, if I push this up with a load of 1, I get this. That means that if I push it up with a load of By, I should get 0. So then I'm going to put here By times that. And that has to be 0, of course. And then from here, we can solve for our By. And our By, once you divide this and you pass to the other side and you divide this by that, you get that By is 1837 kip in the direction that we place it. Now we have By. And from this point on, the problem just becomes, once again, a simple static problem of drawing shear and moment diagram. So let's do it for the sake of doing it. That's it. Now what do? You go back to your original structure. This is my original structure. But now this is a roller. And I know the reaction. I just calculate that reaction. This reaction was 18.37. So then I'm gonna put that reaction here, 18.37, which I know. And my problem is basically how much is this value. Remember, the value that we calculated before as MA is not the correct one, because that value was assuming that the structure was statically determinate, and the value that we calculated for this one also for AY is also incorrect. It was correct for that approach, for that trick that we were doing, but it's not correct for this. So this is 20, this is 15, this is 20, and this is 25, this distance. 25. And now we just do summation of moments. Well, first you can do summation of forces in Y equals 0 if you want to. And if you do summation of forces in Y equals 0, then you get AY. Let's start 18.37 plus AY minus 1.5 times 20 equals 0. So AY equals 11.63. Keep. And now let's do summation of moments at A equals 0. If I do moment at A here equals 0, you have 18.37 multiplied by 20 plus 15. Negative. Minus. That's it, right? Now this one here. Plus. This is 1.5 times 20. This distance 10. So it's going to be plus 1.5 times 20. That's the load. Times the distance 10 plus 15 minus MA equals 0. And then we can solve for MA, which is 107.05, if my calculations are correct. Let me check it because I have been wrong before. Yeah, don't get surprised, guys. I've been wrong before once. I've been wrong once before. And when was I wrong once before? I was wrong once before because I thought I was wrong, but I was correct. 30 times 25 equal 107.05. So this is correct. Good. Okay. Now the next step, enforced members are going to be helpful when drawing the diagrams. I don't have anything concentrated in this joint, so I'm not going to do a special drawing for the joint. I'm just going to do this here. 18.37 right there, 1.5. This distance is 20. That means that I can calculate how much is the force here. The force here at this end is going to be 18.37 minus 1.5 times 20. So that means that I need, in this direction, I need, remember this is 1.5 times 20, which is 30. 30 minus 18.37, 30 minus 18.37, I need exactly 11.63 in this direction. And I can calculate the moment also at this end. The moment at this end is going to be a moment here. Summation of moments here equals 0. Then you have negative 18.37 times 20 plus 1.5 times 20, which is 30. 30 times 10 is 300 plus m equals 0, so this moment is going to be 67.4. Yeah, I get a negative, but then you have to pass it to the other end, positive. And there's no horizontal force, obviously, here. And now we have to transfer those forces here to this beam. The 67.4 is going to transfer like this, no problem with the moment. And now that force over there, this force, is going to be transferred like that, 11.63. And then we go back to the same conversion that we need, this conversion and this conversion here. Now we know that this angle here is 53.13, 36.87, 53.13 is that angle again, meaning this force here, the vertical force, then this one here is going to be 11.63 sine this one. Remember, that angle over there is the same angle as here. So that one over there, 11.63 times sine 53.13, that's 9.304, and this one here is going to be 11.63 times cosine of 53.13, and cosine of 53.13 is 0.6. So this value here is going to be 0.6 times 11.63. So that means that this value here is 6.98, right there. And I don't have anything else here. I have that moment of 63 over there. So if I go back and I try to switch this, I knew this was 11.63, but now I have just to compensate for these forces at this end. This force was pushing it down, so this force is going to be like that, 9.304, and this force was like this, so this force is going to be like that, 6.98. The only thing that we have to calculate is the moment at this end, the moment. I'm going to use another color because this is getting, this moment here is the one that I have to calculate. Summation of moments here, so I have negative, I have 6.98 positive, 6.98 times this distance, which is 25. 6.98 times 25 minus 67.4. That's 106. 106.35. I think that's, there's some errors here, but the errors are in the rounding. 6.98 because it's not exactly 6.98. 6.98 times 25 minus 67.4. Yeah, 107.1 here, the moment. And once we have this, everything is ready for our shear moment diagrams. So let me put this here, and let's start with my axial diagram. First one is the axial. Axial. No axial force, meaning this is going to be like that. Now here in this case, I have an axial force this way, which is compensated by an axial force in this way. So the only thing that I'm going to have here is this value is 9.304, and the whole thing is going to be in compression. So this is going to be in compression. Now the shear diagram is going to be something like this. Let's start with this part. 18.37, 18.37, jump, 18.37. Now, I find this other force, which is linear and which is 30. I should go to negative 11.63, straight line, like that, straight line. Find this 11.63 that push it up, close, small yes. Go to this other one, 6.98, 6.98, positive, negative, 6.98, negative. Remember my XY is like that, so if I'm going down in this direction is negative, and it's gonna come all the way constant, there's nothing else up to this point. Find this force pushing it up, and now you can say your small yes. We have to calculate that point. That point, if you use the approach that I explained you before, you can draw the line here, the parallel line, whatever, but at the end is the same thing as dividing both by this. So this is going to be equal to 12.25. And now we'll go to the moment diagram. The moment diagram is going to be go to this point. Is there any concentrated moment here? Nope, because it's a roller. It starts with 0, so it's going to start with 0. And then I get this positive area. How much is that area? 18.37 times 12.25 divided by 2. 18.37 times 12.25 divided by 2. 112.52 at that point. So from here to here, 12.25, I'm going to get 112.52. And this is, remember the circle, remember the Alamo. Please don't neglect infants, neglect the dumb people instead. Positive decreasing, positive decreasing, positive decreasing it is. Now for the other part, which is this, then if the total distance was 20, and this is 12.25, then this other distance is going to be 7.75. I had that 112.52 minus this area, minus 7.75 times 11.63 divided by 2, and that's going to be 67.4. 67.4. So I'm going to reach this point, positive 67.4. Negative increasing, negative increasing, negative increasing, like that. Now we go to this point, and as you can see here, where are we? Here. You see, this is the moment that we have, and it's coming in this direction, meaning this is gonna close like that, 67.4, pushing it down to 0. Yes. Now we go to this other part, and in this other part, as you can see, we start with a push up, 67.4. It has to be the same one, except that you have the third leg. If you have a third or a fourth leg, then the summation of all of them, this is what is going to change things. So this is 67.4 right there. And now I have this negative diagram here for shear, and this is 25, remember, the total distance. And this value was 6.98. So it's going to be 67.4 positive minus 25 times 6.98, and that's 107.05. So 107.1 negative, negative 107.1, and this is straight line here, meaning this is going to be constant, this part from here to here. Assume that this is a straight line, and then we find at this end this moment, which if you look at this end is going to go in that way, and it's going to push it to 0, and then we can say yes. I'm sorry, this is too small. And in case that you have any doubt, that means yes. So I hope that you like this problem. This is a complete problem, very complete problem. It can be done faster, but I'm just explaining you all the details. So keep practicing, guys, and I see you in the next video, or better say, you will see me in the next video. Bye.